Somewhere out in the dark, dead celestial cores are violently erupting, aiming concentrated beams of high-energy radiation directly at Earth. This is an active, everyday reality of the cosmos. Right now, thousands of these invisible radiation beams are washing over our planet. We know they are there because we can track their highly rhythmic signals. When astrophysicist Jocelyn Bell Burnell isolated this precise data pattern in 1967, it provided the very first proof of these deep space emitters. If our planet is constantly swept by X-rays and gamma rays from these dead stars, we have to ask why life hasn't been wiped out, and what happens if one of these sources drifts into our neighborhood. To understand our cosmic safety, we first have to look at the violent physics that forge these stellar weapons. A star much more massive than our Sun reaches the end of its life when its internal nuclear fuel runs out. The outward pressure of fusion stops, gravity takes over instantly, and the massive blue giant collapses inward, violently rebounding in a chaotic supernova. The explosion blows away the outer layers, leaving behind a neutron star. This is a crushed dead core that packs the entire mass of our Sun into a sphere roughly the size of a city. Angular momentum forces the compressed core to spin hundreds of times a second. This generates magnetic fields billions of times stronger than Earth's, funneling charged particles to the poles. Blasted near light speed, the core sweeps twin beams of powerful X-rays and gamma rays outward. The death of the star doesn't end its influence. It leaves behind a highly active, weaponized core, perfectly capable of catastrophic damage if a planet falls into its line of sight. Consider the impact if a rogue pulsar drifted into our immediate stellar neighborhood, within a 10-light-year radius of Earth. The immediate threat is chemical. Instead of thermal heat, the beam triggers a catastrophic reaction in the upper atmosphere. The intense bombardment of high-energy radiation would slam into our atmosphere, ripping apart the bonds of nitrogen and oxygen molecules. As they are forced to recombine into nitrogen oxides, our protective ozone layer would rapidly dissolve. Stripped of our atmosphere's natural shielding, the lethal ultraviolet radiation from our own Sun would pour down onto the surface. This unchecked solar exposure would sterilize the planet and instantly collapse the base of the global food chain. The situation degrades even faster if we introduce a magnetar, a hypermagnetic cousin to the pulsar. If its massive magnetic field were to violently snap and realign in a starquake, it would unleash a gamma-ray burst, instantly stripping the atmosphere and flash-frying all biology on the facing side of the Earth. At close range, the cosmos doesn't need a physical collision to destroy our world. It only needs to strip away our chemical shielding to guarantee total extinction. Fortunately for us, the closest known neutron star is located roughly 400 light-years away, and its extreme beams aren't even pointing in our direction. Our primary defense against these violent phenomena is the sheer, massive emptiness of space. As a pulsar's X-ray beam travels thousands of light-years, the raw energy spreads out, drastically weakening in intensity. By the time those diluted beams reach our solar system, they are merely a microscopic tickle of radiation that our atmosphere brushes off effortlessly. Our solar system resides in a remarkably quiet, empty bubble of the Milky Way. This physical isolation reduces the odds of a rogue pulsar threatening Earth to virtually zero. Because this vast distance turns these planet killers into precise rhythmic flashes, humanity plans to map them. Future spacecraft will use these exact signals as a galactic GPS system to navigate the deep space between stars. The universe is filled with intense destructive power, but the massive scale of the cosmos takes the deadliest weapons it can forge and transforms them into the very lighthouses that will safely guide us into the dark.